Our objective is to design self-assembling and self-reconfiguring robot systems. These are modular robots with the ability of changing their geometry according to task. And this is exciting because a robot designed for a single task has a fixed architecture, and that robot will perform the single task well, but it will perform poorly on a different task in a different environment. If we do not know ahead of time what the robot will have to do and when it will have to do it, it is better to consider making modular robots that can attain whatever shape is needed for the manipulation, navigation, or sensing needs of the task.
Up until now, most other modular robotic systems use servos and motors in order to have arms and attachments that move modules into different places. However, we wanted a simpler approach that uses fewer actuators, fewer moving parts, and was easier to implement on a lot of different robots. And so the approach that we chose is to use angular momentum. And essentially what that means is there's a spinning mass that spins inside of the robot. When we want the robot to move, it stops that spinning mass, which takes that motion from the mass and applies it to the robot. And a part of this that's unique is that the spinning mass is completely inside the robot, and so the robot doesn't have to be in a certain position in order for the force to be acted upon the robot. And so this allows for a lot more types of motion with only one actuator.
So there were a couple challenges when we came to design the M-Blocks. One was fitting everything inside. So we have a relatively small volume, and we needed to fit a brushless motor controller, a flywheel, a braking mechanism, electronics, a radio, a battery. Additionally, we faced the challenge of trying to simplify and make the design as robust as possible. So we didn't want any external moving parts, we didn't want latches, we didn't want the cubes to change their shape. We just wanted simple blocks that were able to move on their own. The magnet system in the cubes is one of its key features. So we have face magnets. There's 8 face magnets that provide some coarse alignment. And then there's these edge magnets, which are free to rotate. And the key is that when a cube starts rotating, the edge magnets actually get closer to one another. So if we start from this configuration and we break the face magnets free and start rotating, the edge magnets actually get a little bit closer due to the fact that the edge is slightly cut back or chamfered. And as a result, you form a very strong bond between cubes, which allows them to stay attached as one is rotating into a new position. It continues rotating, the face magnets provide alignment, and it snaps into place.
One other benefit of having an inertial actuator is that the cubes are able to jump, and this is a capability that very few robots have, and especially very few modular robots, because in order to jump, there's a requirement for a very high amount of energy in a very short amount of time. And most robots are optimized for control, stability, and precise motion. In our robot, we found it kind of as an accident that they're able to jump. We weren't intending to do that, but it ends up that we need enough momentum inside each cube in order to move on a lattice structure, which is what we intended, that we can also, when we apply as much energy as possible, it can jump through the air, which is pretty exciting because it also allows robots to jump on top of each other and to go places that they couldn't go if they were only moving directly on the structure.
Currently, we're sending commands to the modules with a radio. So we type commands on our computer, those are transferred over a wireless link, like your Wi-Fi system in your house, and then the cube responds to that. In the future, we envision putting the algorithms on the modules themselves so that they completely autonomously, in a distributed fashion, decide how, when, and where to move. So we want to be able to take a large group of cubes and tell them, form this shape, and give those instructions at a very high level, and then have the cubes decide on their own how to go about accomplishing that task.